5. I tend to think that 5 is already a big number. Seriously, if I see 5 cards, I can't count them all at once. I need to separate them into a set of 2 and a set of 3 or something like that. I don't know if you're the same. But anyways, that's not the kind of big numbers I want to tell you about today. I want to tell you about numbers that are so big that they do not sound like numbers anymore. Let's start with a glass of water. The number of water molecules in this glass is around 10 to the 25. That's a 1 followed by 25 zeros. Now that's a big number, a really big number. It's literally an astronomical number. Roughly, it's the number of stars in the universe, more or less a few zeros. In fact, there are so many water molecules in this glass of water that almost surely some of these molecules, actually many of them, were in Jesus' last cup of water, assuming Jesus drank water. Indeed, the ocean around the Earth is roughly 5 kilometers deep. Since the Earth is roughly a sphere of radius 6,000 kilometers, this means that the water on Earth represents around 5 times 4 pi times 6,000 square, which is about 100 million kilometers cubed, which is 10 to the 20 liters. Roughly in a cup there's like a tenth of a liter, so there are roughly 10 to the 21 cups of water on Earth, and I have one of them, so 1 out of 10 to the 21 water molecules on Earth is actually right here. Now, in Jesus' last cup there were 10 to the 25 water molecules, which means that, assuming that they are all well mixed over the last 2,000 years, roughly 10,000 of the molecules in here were in Jesus' last cup. Of course, all the calculations I've made are very rough, but this should give you an idea about how just counterintuitive such huge numbers are. They are at the limit of the understandable, literally. Today, we know about 10 to the 14 digits of pi, and I'm confident that in a few years we may get to 10 to the 25 if not more, but I'm pretty sure that we'll get stuck around these amounts simply because writing down the digits of pi takes time, and there's only so much time in a lifetime. There are 10 to the 7 seconds in a year, so even with a billion of operations per second on a billion computers, we can only write down 10 to the 25 digits per year. So 10 to the 25 is a big number. It's basically the limit of big data. But for a mathematician, it's still a small number. Even a number like a Googol, that's 10 to the 100, that's 1 followed by 100 of zeros, that's still not such a big number. Yes, it's bigger than the number of particles in the universe, but mathematicians couldn't care less about the universe. For instance, if I take a set of 78 cards, the number of possible shuffles of these cards is already bigger than the Googol. And 78, that's a very small number. In fact, in combinatorics, that is when we try to count the number of possible arrangements of something, a Googol is quite small. Instead, we quickly get to numbers like the Googolplex. Googolplex is 10 to the 1 Googol. It's a 1 followed by a Googol amount of zeros. It's huge! You can't even write down this number in our own universe because there are more zeros than the number of particles in the universe. But even that doesn't do justice to just how big this number is. As explained in this Numberphile video, if I walk a Googolplex of meters in this direction, I should meet at some point an identical copy of myself. This is because the Googolplex is much bigger than the number of possible arrangements of particles in an amount of space that's the size of my body. So just by pure chance, it's highly likely that out of the Googolplex of sizes of my body that I'll encounter, there will be at least one that's identical to my body. And that's super weird. I mean, if that guy over there is exactly like me, why is he not me? What is the difference between him and I? I mean, we are exactly identical, both in terms of biology, chemistry, or physics. We look the same, we smell the same, we think the same way. I mean, if you were to replace me, you wouldn't even notice a thing. No one would. Really, the Googolplex is a number that's just beyond the understandability of theoretical physics. And yet, the Googolplex is still ridiculously small. In the realm of mathematics, let's now talk about Graham's number. In the 70s, Ron Graham introduced a big number to prove the theorem below. It's not such a complicated theorem. I mean, Ron Graham explained it himself in this video right here, but I'm not going to explain it to you now because I don't want to end up like Matt Parker on this Numberphile video.
People appear in... I forget.
But I will have you noticing that the only number that appears in this theorem right here is the number 4, which is smaller than the first number I told you about in this video. And yet, to prove this theorem, Ron Graham had to introduce this mind-blowingly big number that's now called Graham's number. In fact, it's so mind-bogglingly huge that if you were to try to remember all the digits of this number in your head, at some point your head would have to turn into a black hole. It has to do with black hole entropy. Anyways, the limit of information that your brain can contain is extremely huge, but it's really nowhere near the number of digits of Graham's number. So what is Graham's number? Well, the first step to compute Graham's number is to compute this number right here, 3 arrow, 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 3. And what's that? I have no idea. It's just so huge. Let me instead focus on 3 arrow, 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 3, which, as you'll see, is already much bigger than the Googolplex. So, what do the arrows mean? Well, the 3 arrows mean that this expression can be decomposed as a sequence of 2 arrows. Next, the left 3 means that the 2 arrow sequence will only feature 3's, while the right 3 means that there will only be 3 3's in this expression, so that 3 arrow, 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 3 is 3 arrow, arrow, 3 arrow, arrow, 3, where the parentheses start on the right. Now, this quantity corresponds to 3's separated by single arrows. How many 3's are there? There are 3 arrow, arrow, 3 3's. Now that's 3 arrow, 3 arrow, 3. Finally, we have decomposed everything into single arrows. So what's a single arrow? Well, it's an exponentiation. So that 3 arrow, 3 arrow, 3 is 3 to the power 3 to the power 3. That's 3 to the power 27, which is about 7,000 billions. Pretty huge, huh? Well, that's nothing compared to 3 arrow, 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 3, which is a column of 7,000 billion 3's. This is already a stupidly huge number, much larger than the Googolplex. Remember, the Googolplex was only a piling of 3 exponents. Here we have thousands of billions of piling of these exponents. And yet, remember, these are just 3 arrows. It's not even the first step of Graham's number, which was 3 arrow, 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 3, 4 arrows. And you've seen just how fast number grows when you just add 1 arrow. I have no word to describe this number G1 right here. And yet, remember, it's just the initial step to construct Graham's number. The next step is, well, you take as many arrows as G1. You take G1 amounts of arrows, and we had just 4 arrows. We couldn't explain this number, and now we have G1 numbers of these arrows. So more generally, when you construct Gn plus 1, what you're going to do is to take Gn arrows between 2 3's at the 2 ends of this huge stack of arrows. And eventually Graham's number is going to be obtained at the 64th iteration. It's G64, which means that it's 3 followed by G63 arrows and then another 3. It's stupid. It's stupidly crazy. It's nuts. It's completely dumb. It makes no sense to me, and I don't think it should make sense to anyone. Here we are way beyond the realm of mathematical understandability. It's even doubtful that logic still applies to such numbers. But even then, Graham's number is still just a finite number, which means that there are infinitely many numbers that are much bigger than Graham's number. So to answer the original question, how big can numbers be? Well, surely they can become overwhelmingly huge for our teeny tiny monkey brains. But in the realm of mathematics, there's no such thing as a big number. Whatever number you can come up with, it's still going to be ridiculously small compared to almost all of the numbers, because there's always going to be only a finite number of numbers of the same order of magnitude or smaller than the number you're thinking of. And there will be infinitely many numbers that are just so much bigger than the number you're thinking of. The point is, seriously, how can we know that logic still applies to these stupid numbers? Hey, so I hope you've enjoyed this video. Next time we're going to talk about Zeno's paradox. In particular, the question I want you to think about is, do we have 0.999 repeating equals to 1? And why would that be true? And why would that not be true? This is what I want you to think about. And it will lead us to talk about infinite sums, which are a very important tool in mathematics that involves infinity. So if you've enjoyed this video, don't forget to like this video, subscribe and share this video, and I hope I'll see you next time.